Welcome everyone. I'm very happy that you came here for my presentation. It's not that easy to find room number five, so the fact that you appeared here means that you are quite motivated to hear my presentation. And today's topic is Serverless Jenkins DevOps pipeline with Kubernetes and Spark. Quite a long title, but I'm going to explain every part of it during my talk. So a few words about me. My career is mostly about JVM-based languages. Firstly, I work with Java. Now I'm working with Scala. And currently, I'm working at Virtus Lab. It's a Krakow-based company, but it's partially a software house, and it gives its services to other companies. And so I'm working as a part of Virtus Lab for Tesco Technology when I'm a part of data platform team doing big data. Okay, so what's the story behind my today's talk? For the last 8 months, I was working on something like internal tool for ingesting data. So this is one of the main topics of big data that first, before you try to analyze it, you need to have it in some kind of data lake, some kind of cluster when all of this data is collocated. And our application didn't have much logic inside, so there were not some complicated transformation, but the main challenge and also the main value of our project was to integrate with various services, specifically the source services like Teradata and Oracle, on which online services were running and storing their online data, and we were integrating with them to smoothly copy the data from these databases to Hadoop platform, because Tesco has a data lake implemented in Hadoop. So in general, in big data, integration is something that you challenge every day. Another thing is that, as in many big companies, there are communication problems and many procedures that are often difficult to tackle. And what we suffered from is that we couldn't communicate with the teams that was handling Tesco Jenkins to get more resources for our jobs. So we're facing problems with very long delays on our builds. That was very slowing down our progress. And the last thing that happened is that Tesco decided to go for Azure. And one of the features of Azure is that it provides Kubernetes that is finally pre-configured and quickly to start. And all these 3 things led us to make an effort to implement DevOps Jenkins pipelines on Kubernetes. And that's what I'm going to talk about. But before we start, a few points. This is a story about a real implemented solution, not only a plan or a vision of solution, but factual implementation that provides value. Another thing is that this talk is out of methodology and culture track. So I will not be talking only about technical implementation, but I will also focus on good development practices that drive us in our effort to create this pipeline on Jenkins. Those good development practices are rather well known. Everyone agrees on them, but really hardly anyone follows them. So I'm going to talk how we followed them. And the last point is that probably I'm going to cover some basic concepts that you are familiar with. But I believe that even if you know something quite well, and you hear somebody else describing this thing from some other perspective, you can still get some value, you can get better understanding of what you already know. Okay. So let's start. Let's start with continuing integration. Continuous integration. Is it quite an old concept? that addresses the problem of integration hell. So very early, developers find out that what is really a difficult thing in their work is to merge the independent work of different developers. So this is something that we know very well. Probably anyone here sitting had some situation like this before. Many files with conflicts, and you need to spend a lot of time fixing these conflicts. So the concept of integrating, and what's more, the bigger the changes, the harder it is to merge. And this difficulty of merging is not increasing in linear way, but more in exponential one. So when the change is twice bigger, it's often 4 times harder to merge it. And the concept of continuous integration is very simple. So if the big changes are difficult to merge, let's merge smaller ones, but very often. And the concept even says, let's merge continuously. But what would it mean to merge continuously? It would mean merge all the time. Everything that you added is already integrated. So it's not quite feasible, because if we wanted to really integrate continuously, we would need to have a tool, something like Google Doc, when you have real-time multi-edit mode. So many people working on the same text, so added changes are already integrated. So it's not quite feasible, but what is feasible is to integrate at least very frequently, merging small changes. Okay, so when we need to integrate very frequently, we need to also very frequently build and test. So continuous integration has a need for automation tools, and that's why tools like Ant, Maven, Gradle, SBT appeared. And not only that, but also things like automation big servers appeared, like Jenkins. Probably everyone here knows it, just to facilitate this practice. The next step after continuous integration is continuous delivery. So first, what does it mean to deliver? We deliver features to our clients. So to deliver feature means that our feature is coded, it's released as in new version of software that includes this feature, and it's given to a client. So we can say that continuous delivery addresses the problem of release hell, like continuous integration addressed integration hell. So what it means, that we change our way of working from the way that we work in intervals, that, for example, we code for 1 month, and then for 1 week we are trying to release what we coded. And we change it into the way that every small change that was coded is just after it's merged, it's being merged to the release branch, and it's ready for release. So the concept says, again, let's deliver continuously. And it's still something that is quite figurative, because if we wanted to deliver continuously, we would need still to have something like Google Doc with an option that at any time we can export our work as PDF. So even if we are in the middle of the feature, some release guy can click and download this as a package. So still, it's not quite feasible. So we are not delivering continuously, but we are delivering very frequently. And you may also say, OK, but when I have quite a big change, I can't divide it into small pieces to be released. For example, we are creating a form for user input data, and we can't just provide firstly one input, then a second input, and then submit button. Either we give everything to client or nothing. And so there are some good practices that continuous delivery invented. For example, feature toggle. So when you are starting working on some feature, you just embrace the unfinished work in condition block. So this condition says if the package is run on dev environment, render the feature. If it's run on production, hide the feature. And this feature toggle is disabled until the whole feature is ready. OK. So for sure, continuous delivery introduces some overhead. You need to do more work that you would that you needed without continuous delivery. So what it gives us? First of all, the time to market is decreased. And it's very important for our business because what we do as software developers, as developer companies, we are developing products. We're not coding for the code itself. And why continuous delivery decreases the time? It adds more work to do. But an overall time is decreased because you can find bugs earlier, and in this way, they are more easy to fix. When you are testing every single commit in the whole, and you find that this commit broke some functionality, you are still in the context of the change. So you more quickly can fix it. And what's more, you know that this particular commit caused the problem. When you work in intervals and you, for example, release quarterly, and after 3 months you find out that some feature is broken, you need to first find which commit introduced the bug. It could be mine commit or commit of some other people in my team. And then you need to get into the context of the change that caused this bug. So in general, you can resolve bugs much quicker. And other thing is that you get the feeling of you get the state when the release is no longer a pain. I can give you an example from my previous work. There was some conference where our managers wanted to present their product and a new feature that was vastly advertised as some milestone step in the product functionality, and the whole team was really putting much effort into developing it. But we were not doing continuous delivery, so the tests were deferred till the release day. And the conference was in 2 days, and our manager found out that one of the core features stopped working. So we added new functionality, but they broke some others existing. And it was very difficult 2 days for the whole company. OK. So we know that continuous delivery is something that provides value. How to implement that? How to make it working in our company? So what's at the foundation of this methodology are tests. So test that needs to be fully automated. Imagine that you're testing fully your application right after each small change merged to master. You would need to have many test people in your company, probably more than software developers. That's why you need to automate your test. Your test needs to cover all functionality of your software. So just to avoid situation like in my previous company when a new feature broke something that already worked. And of course, tests need also cover integration with external services. It's not enough that our application is fine inside, but we also we need to be sure that it's working perfectly with third-party services. And probably you know that because you're software developers, such tests are very heavy and take long time. So if we really want to continuously deliver, you would need to have big resources for test execution. That's why an accepted way of implementing continuous delivery is not delivering each commit, but delivering, for example, daily or twice a week. So still, when for example, the whole test pipeline is run during the night, the next day I quickly find out that my change broke something, and I'm still in context of this change, and I can fix it quickly. And a next step after continuous delivery is continuous deployment. So it basically covers all the things of continuous delivery with the exception that at any moment the package is not only ready to be released, but it's factually released. Yeah, you're adding a change, and your change is deployed either to production or to some early access environment for end users. And still, can we have continuous deployment? It's not feasible as in previous cases, because that would mean that we code something and this code is hot swapped at the production. And what we'll get, that user gets error at a random moment. OK, so it's not continuous, just frequent enough. And the last thing on my list of good development practices is DevOps. So DevOps is quite, it falls in other group of practices than CI/CD. But let's describe it. DevOps says that we should bring development and operations very close to each other. So what is development? Development are those guys who are creating products, so product makers. Guys who probably work with some code editor, so software developers, QAs, designers, UX guys. And operations are those people who take care of product after its birth. So when it's created, they just take care that it works correctly. So they probably spend more time with console, monitoring some servers. And here we have administrators, security guys, network guys, and other people who take care of the life of the already born product. So how to implement DevOps? We should have cross-functional teams. So the teams that they are not divided by people who create software and people who maintain it and deploy it, but we have all these people together in one team working very closely. And what's desired state is that skills of developers and skills of operational guys are overlapping each other. So the developer is aware how the code will be deployed, and also the operational guy knows how it's coded. And the desired state where DevOps would like to go is that those skills are merged in one person. So a person who knows very well how to code, and a person who very knows also how to deploy what he coded. And such person we can call DevOps. OK, and still, why DevOps? Goal is very similar to continuous delivery. Goal is to reduce time between the change commit to the code base and the time the change is deployed to the production. So if the DevOps is so close to continuous delivery, what's the difference? Yeah, and one thing very important is that the time is shorter, but the quality is still the same. It's not like I code and recklessly deploy. So what's the difference between DevOps and CI/CD or continuous delivery? Continuous delivery refers to development cycle, so basically how you produce code. DevOps refers to culture of organization, culture of working. So DevOps more focuses on the roles. But basically, they cover the same problem, but from different perspectives. OK, so that would be all from the good development practices that I'm going to cover today. And let's talk about the context in where I'm working. So a question to you. How many of you work or worked in the past in big data? Few people, rather minority. And OK, so it would be good to just say a few words about big data in general. So what is big data? And as you probably guessed, there's no a given size of data at which the data becomes big. It's more complex thing to describe big data. The common definition is that big data starts at the point where the data is too big or too complex to be analyzed by the traditional software for data analysis. So when we have some spade and we want to dig in at big desert. So what is this traditional software for the data analysis? These are relational database management systems. These are some libraries to be integrated in applications, or some desktop application like Excel. So when the data what influences the size of the data at which point it becomes big is how complex is the computation that we are going to execute. If it's some simple transformation, the data, very large still is not big data. But if it's a complex one, when we, for example, need to sort data, to search it in some way, then even a small piece of data becomes already big data. OK. And important thing is that big data is not only about the size of data, but also about its complexity. And that's why distributed computation and more flexible way of defining this computation is a way to go. And for this reason, a framework like Hadoop appeared. Hadoop is a framework for distributed processing and storing data. So there are two core parts of Hadoop. This is HDFS, which is distributed file system. Why file system? Because you can have many different kinds of data, and the file is the type that can generically store any kind of data. And you have also Yarn, that is a resource manager. It gives an API for other tools to reuse the computational resources that are available in cluster. And on the top of Hadoop, there are many tools that uses these two core features, like Hive and HBase. And there is also Apache Spark that is currently a way to go to cope big data. So Apache Spark is independent from Hadoop, but it integrates with it very well, and it's widely used to process data on Hadoop. So we were talking about good development practices, and we found out that what's at the foundation of these practices are tests, and how testing looks in big data. So unit testing. What can be a unit in our big data programs? So typically, big data program is some kind of flow that you read data from some source, you apply some transformations, aggregations, and you get the result. So a good candidates for units are those transformations and aggregations. And it is quite easy to test it. So in general, unit testing is easy. In big data, it's still easy. What about integration testing? Integration tests in general are of two types. One of the types is that it tests if the modules of our application works smoothly with each other. So we have big applications, many modules, and we develop it independently, and we just want to make sure everything works as a whole. And the second type of integration test is that our application works fine, and we need to make sure it works fine as well with external services. And that's the most important case in case of big data, because big data applications, specifically Hadoop applications, needs to integrate with many services, like our ingestion tool application. So mostly the bigger challenge of the logic inside big data application is the integration part. So the test should mainly cover integration. And you may ask, okay, so why is the integration a big deal? You just add a connector, a client to some service. Well, you configure it, it should work. Well, it should, but what's specific for Hadoop cluster-based application is that normally Hadoop cluster gets upgraded, and all the versions of software gets upgraded as well. So you need to periodically check if your application still works okay with the cluster. And it's not only bumping a version of the client, it's also sometimes adopting properties, adopting some configuration. So this should be covered by the test. And it's difficult to set some tests because you have many services to set up for testing environment. And that's why continuous delivery is often given up in big data teams. But this talk is about different story when we put effort to stick to continuous delivery and overcome the problems. Okay, a few words about Jenkins. I'm not going to talk for long about it because probably all of you know it very well. But just a few things that will be needed for the explanation of former things. So Jenkins is an extensible automation server. So it has possibility to automate builds, tests, also deploys, and it's extensible. So Jenkins architecture is a plugin architecture. The core is very thin. It just provides a web server and an API for plugins. And what really gives life to Jenkins are those plugins. You can't really utilize Jenkins without them. And what's another important thing is a Jenkins master-slave architecture. So there is a segregation of responsibilities. There is a Jenkins master. There's one Jenkins master that stores configuration of the builds, that orchestrates where the build is executed, and that also stores some history of the builds. And there are slaves who are the instances to factually execute the job. And what's possible in such configuration is that you can have different environment setup for different slaves. So you can have, for example, you have Jenkins for the whole company, and you have teams that work in Java that will need Java configuration on the slaves, and you have, for example, teams that work in Python, so you would need to set up Python on the slave. So that's possible in Jenkins. Creating configuration for a build, you specified where you want to run this build, so at which slave. And how those slaves are set up. So there are two main ways to set up slave and connect it to Jenkins. The first one is that you put all required information like address and credentials, and Jenkins SSH to a box where it spawns slave, or you manually SSH node, start their Jenkins agent, and gives Jenkins agent an address of Jenkins master so that it can register itself. And there is a newly created third method of spawning Jenkins slave that utilizes Kubernetes. That's what I'm going to talk to you about today. Okay, so who of you works with Kubernetes? a bit more than with big data. Cool. So just to give a sort of description of Kubernetes to those who don't work with that, Kubernetes, it's an orchestrator for deploying Docker containerized applications. So Kubernetes is a tool that manages that when you want to deploy a container to a cluster, Kubernetes takes care where it factually will be run. So we have a cluster of 6 nodes, and Kubernetes takes care where those containers land. And what's important, Kubernetes doesn't implement its own containerization engine. So, and it reuses existing ones, typically Docker, or it can also use RKT. So the important thing is that Kubernetes doesn't replace Docker, it uses it. And so in this way, it's very similar to Docker Swarm, but it gives more features. For example, load balancing. When we have our container replicated, Kubernetes can load balance can balance the load to those containers. Kubernetes has a functionality of managing unhealthy nodes. So let's imagine that one of the nodes just breaks down. We have container running there. Kubernetes will take care of moving it to another healthy one. Kubernetes supports automatic upgrades and rollbacks. So you don't need to manually change the version of container, just specify, please run the current version of it, and it takes care of it. And what's very cool about Kubernetes and handy for programmers, all is done in declarative way. You do not need to implement logic of upgrade or of running a container. You just give specification, I need this container run 3 times, and Kubernetes takes care of that. And a few more meta info about it. It's open source, started by Google. Kubernetes means helmsman from Greek. Do you know what helmsman means? A person who drives a ship. And it's often abbreviated as K8s. And why is it that? Because between K and S, there are 8 letters that are just replaced by digit 8. OK, so basic terms about Kubernetes. We have nodes. These nodes need to have some containerization engine, like Docker. On the nodes, what is deployed are containers. So these are typical Docker containers or containers from other engines. But the smallest deployable unit is pod. So container is deployed to cluster as a pod. So inside pod, there can be more than 1 containers, but it's rather discouraged. The only legitimate situation when you should have more than 1 is when 2 containers work closely with each other. So for example, you have some web application that has some cache, that is external cache. It's good to just have them together. And pods is some kind of logical environment for container, and each pod has its own IP inside cluster and also has a port space. So you can't run 2 containers inside pod that will take the same port number. And apart from pod, we have services. Service is a way of abstract way of exposing your container or your application outside. The important thing is that pods are mortal. So, for example, this node becomes unhealthy, and this pod needs to be rescheduled to other node. And it's done in the way that the previous one is killed, and the new pod is created, which means new IP address is assigned. So if you want to just have a stable reference to some service, to some functionality, some application, you need to create a service that points to given container, to given pod. And service takes care when the pod is killed and restarted, it's still exposed it under stable host name, for example, like here, service name and the port. And what service can also do is load balancing. You can have replicated pods, and service can load balance between them. Okay, and there is also a CLI for work with Kubernetes. So basically, I will show some basic commands. As I said, configuration of Kubernetes is declarative. And to set something up on Kubernetes, you just create a YAM file that describes what you want to have configured. And the most basic command is just you apply this config file to a cluster, and Kubernetes takes care of rest. You can list things that are running, like nodes, pods, services, and so on. And you can, of course, delete. And what is very handy for people who already work with Docker is that kubectl implements also a Docker syntax, let's say. So if you change here kubectl to Docker, you have a valid Docker command. So we can just quickly run some image on the server. OK, so imagine that you have many services that you need to set up, and they need to work together, and you want to somehow manage them all. So there is a space for a tool that would manage it. And there is such tool, it's Helm. So it's some kind of package manager for Kubernetes. Oh, the wrong direction. So so yeah, it manages deployment of sets of containers. So as I said, everything is configured in Kubernetes as a YAM file. So when you have many services, many applications, you have a lot of YAM files. You probably need to wire them with each other. So some kind of templating and sharing variables is needed. And that's what Helm provides. And what it does as well, it also provides functionality of packaging the whole configuration so that you can refer to one of the previous versions of your whole deployment. OK. And a Helm package, so yeah, this configured whole is called chart, Helm chart. OK, so enough of all this introduction of technologies. Let's get back to what we implemented. OK, so we implemented Jenkins on Kubernetes. So how it works? It works in the following way that if Jenkins has no jobs, no slaves are existing. If there is a new job to run, for example, there is a pull request, we need to compile, test, check syntax, check the styling, then Jenkins master requests from Kubernetes to create a slave, and it's created on demand. Every build gets its own slave, and the slave can live for some interval of time after the build is finished so that it can be reused. So here we can see that the resource consumption is on demand. And question to you, what's the name of such paradigm when you allocate and consume resources on demand, like event-driven, in event-driven way? There's a common buzzword for that. Anyone has idea? Not that. It's called serverless. So you know think about AWS Lambda, but that's the same concept. Your application still provides functionality, but when the load is bigger, when the request comes, resources are allocated. The same in here. Jenkins provides its functionalities. There is a build, resources allocated by means of Kubernetes. OK, and what's important here, because the slaves are spawned dynamically, there need to be spawned from the image that contains all the configuration that our build needs. So when we are compiling Java, we need to have Java compiler installed inside the image that is spawned. Okay, so we have Jenkins in Kubernetes. We have our slaves, Jenkins slaves on Kubernetes. And what's important, there is connectivity between Jenkins slave and the whole cluster. So how to utilize that? We created a Helm chart, so Kubernetes configuration of services, for minified version of Hadoop cluster. So as you remember, our application, that ingestion tool, integrated with many services. And to test this integration, we needed these services to be up and running for test. So we created a configuration of some mini Hadoop cluster with services up. And so tests that were run on slave could connect to those services and execute its logic. So we get a possibility to run integration tests that covered our core functionality, and so we could adopt continuous delivery. Okay, we have 10 minutes left. I'm going now to show how it looked in practice. So let me show. Is it big enough? But you mean this or this? Both, probably. Now it should be better. Maybe white mode? No, it will burn our eye. Okay, I think, okay, so first of all, so to deploy anything to Kubernetes, you need to have a Docker image for that. So we prepared a Docker file for Jenkins master. And what's important here, we have whole configuration of Jenkins master. And what's important is that we didn't want to set up per Jenkins and then configure it manually. We just wanted to make it automated, that when we run it, it has everything that it needs, and particularly that it has, among plugins, Kubernetes, okay? So this Docker file just builds an image that we want. And apart from Jenkins master, we needed a Jenkins slave. So we created a separate Jenkins slave, a separate Docker file for Jenkins slave. So you have images, you want to deploy them to Kubernetes, but look, you're not sending to Kubernetes any binary files. You're not sending Docker snapshots. You're sending configuration, and configuration specifies the image to use. So there needs to be some registry from where Kubernetes can download those images. And so on Azure, we created a registry. So we build images locally, uploaded them to registry. We also created a Kubernetes cluster. Okay, and I have my local machine connected to this cluster. We can get nodes, for example. Why there's only one node? Because the free subscription to Azure doesn't allow for much. So I wanted to just choose a more powerful machine instead for one slave, for one Kubernetes node instead of three or four weaker nodes. Okay, and okay, there are some. And okay, so I had images in registry, so I could run Jenkins on Kubernetes. We prepared a special script for that, Jenkins pipeline setup. So basically, it took a GitHub credentials from us so that Jenkins can be already connected to our repository. And we stored in the secret form in the Helm configuration. And we spawned a Jenkins master that we called Jenkins master. And we can see it. Get pods. Typo. OK, so we have Jenkins pipeline. OK, so that's the one part. And we also needed this minified Hadoop cluster. And that was a bit more trickier. We put much effort in that to configure it. We need to pay attention to have the same versions that are in our cluster in Tesco. So basically, we first prepared quite some images that we customized the generic one to our needs. And so we needed first to publish those images to our Docker registry. And then we created a Helm chart that combined all these images as a whole. So as you can see here, this is this YAM file for configuration. We have here this pod. We have specification. We have containers. And and we have here all these things that we need: Hadoop name node, Hadoop data node, Hive metastore, Hive server, Spike master, and so on. And apart from pod, also a service configuration. And so we had a Helm chart that described all the cluster. So we deployed cluster. As you can see here, we have Spark Hive. We call it Spark Hive pod. And unfortunately, what I wanted to show you at the end is that I make a commit to my code. I deployed it to GitHub. I create pull requests, so the build is run, and the tests are executed using this cluster configuration. But I made a big mistake. Whilst preparing this presentation, I left the configuration of Azure as a last step in preparation, and I found out yesterday in the evening that it's not that easy to replicate the same configuration. So yeah, as you can see here, there's an error in that. But basically, it's probably because of not enough resources in the free version of Azure. Basically, the state that we have is that we have running cluster, and our builds and tests refer to this minified Hadoop cluster during the test execution time. OK, so that's basically it from my side. If you have any question, feel free to ask. You can reach me out after presentation. That's all from my side. Thank you very much.